outside only when you can't socially distance. So that's fine. It's out of an abundance of caution. It's all about equity for PCC. So there are people who legitimately can't be vaccinated, and they're trying to keep them, for now, able to come in, if they need to. But we'll see what happens in the fall. Probably it'll all change, but we'll see. All right, we have a quiz on Wednesday, and I am not going to put polarity on it because we're going to finish up polarity today. So it's really just going to be about drawing Lewis structures and figuring out the shapes. That's all I'm going to make it about, okay? If you haven't been able to do the homework, and I know some people have, but somehow it's not accessible in certain. So on D2L, there's different ways to access these things, and somehow it was accessible to some people, not to others. So if you haven't been able to do that Lewis structure supplement, you do not have to do it. What I'm going to do is I'm going to try to grade it such that the people who actually were able to do it will get the extra points for it. If you didn't do it, I will make the assignment worth less for you, so you'll still get the full credit. You still are welcome to do it if you want some practice. And I'm going to open up the key for it tomorrow after the next class that I have. So it'll all be visible in the documents area. So right now you can't see this one. This won't be visible for you guys. But the regular homework assignment for Lewis structures will be visible. And I'm sorry if it wasn't visible if you couldn't do it, but you can if you want. You don't have to. It's not required. All right. So, man, this is the last week, isn't it? So we'll do hybridization today. This is basically going to be the whole explanation as to how covalent bonds form using the orbitals that we've studied. It's a little bit complicated, but it's not too terrible. It's very visual. And then on Wednesday, we will do a short introduction to molecular orbital theory. We'll do a quiz first, a short introduction to molecular orbital theory, and then we'll just review. And I have to open up the practice exam for the final. I have to remember myself to do that. I don't know if it's visible yet. But we'll look at that later. Anyway, remind me to open it if I don't before tomorrow. Okay. So, I don't know if we're going to review this explicitly, but let's go over kind of some older stuff. Last week we ended the class talking about whether something is polar. I've got some stuff made up. I'll do that later. So to find out if something's polar, we need to know, does it contain polar bonds? And that's not hard to do. You look at electronegativity to do that. But you also have to know the geometry, the shape of the molecule. And so that's a big process. You need to start with the Lewis structure, then from the Lewis structure determine the shape, the electron geometry, the molecular geometry, and then only then can you kind of look at the molecule itself and see if the polar bonds that are in that molecule make the molecule polar overall. So is there an even distribution of electrons? So is it nonpolar or is it uneven? Is there a positive, slightly more positive side, slightly more negative side? And if that's true, then it's polar. Okay. So, I mean, this is the visual part. This is the part that some people have trouble processing in their heads. The molecule is going to be polar if it has polar bonds, and if its centers of partial positive and partial negative charge lie at different places within the molecule. So what I was going to do is I'm going to switch to this simulation thing. This is a PHET website, PhET again. So start off with very simple. These are polar bonds. And so what you have here are two atoms. And we're just arbitrarily setting the electronegativity of these two atoms. So A is less electronegative, B is more electronegative. And because B is more electronegative, the B picks up the partial negative charge, the A picks up the partial positive charge. And you can kind of see that if we make B bigger, the partial charges get a little bit stronger. We're also drawing in this is a fake, but this is the electrostatic potential. This is the red showing where the electrons like to hang out more. Another way to look at it is the electron density map. The darker areas is where the electrons like to hang out more. So for linear, just two atom molecules, it's pretty simple. This is a polar bond, and so this molecule is polar. There is a dipole moment. If I show you the bond dipole, that's the arrow that you could draw. The arrow always points to the partial negative side, the tail is on the partial positive side, and the size of the arrow is proportional to like the strength of the dipole moment. So you can see as we make the B atom less electronegative, closer to the electronegativity A, that dipole moment shrinks until they're the same electronegativity and there's no more dipole moment. It's a nonpolar bond. Okay. So when you get to 3 atoms, it's a little trickier. So here we've got A and C, they're very low electronegativity, and then atom B in the middle is kind of a moderate electronegativity. If I show you the bond dipoles, well, let's look at the partial charges first. The partial negative is on the central one because it's the most electronegative. And the bond dipoles, you can see that you can draw one going this way and one going this way. And this is a pretty flat molecule. There's not anything 3D about it. So you can hopefully see that the overall direction of those two dipole moments from the bond dipoles, they're overall pointing in the up direction. So that yellow arrow represents the molecular dipole. So this is a polar molecule. As we change the shape of this thing, as they go from bent to linear, the bond dipoles aren't changing. It's still the same atoms, whatever they are, with the same electronegativity, but that molecular dipole is disappearing because those bond dipoles just they're canceling each other out. They're pointing in exactly the opposite directions. So when we do the dipole moments, or the partial charges, there's a partial positive here, a partial positive here, and a partial negative here still. But I can't say that one side of the molecule is more positive and one side is more negative, like the opposite side. Yes, the center is more negative, but it has to be one end of it, not the middle, to have a dipole moment overall. So this is nonpolar, even though it has very polar bonds in it. And the hardest part is to look at 3-dimensional, and I have to switch to an older Java-based one. Let's go to real molecules. If I go to something like difluoromethane, which is CH2F2, this has got a tetrahedral shape to it. I can spin this molecule, and there's that tetrahedral shape. This is one way to look at tetrahedral. You've got, 2 pointing this way and 2 kind of opposing that way. The other way to look at it is that tripod with one sticking up, kind of like that, right? That's another way to look at it. It's all the same shape. But if I show you the bond dipoles, there we go. It's a little hard to see here. Let's move this around. The carbon-hydrogen dipole moments are pretty short. Like you can barely see them. And that's because the carbon-hydrogen bond is fairly nonpolar. The difference in electronegativity is about 0.4. We would call that a kind of a nonpolar bond. But a carbon and fluorine, there we go, put these up there. Carbon and fluorine, 2.5, 4.0, the difference is 1.5. That's really a large difference in electronegativity. So these arrows that you could barely see on there are large. And when you kind of consider, well, which direction are these arrows overall pointing in? They're kind of pointing in this direction, to the right here. If I draw in the molecular dipole, there it is. So that's a polar molecule. even though it's 3D. So this is the hardest stuff to see. But again, if you don't like the visuals, if this is hard to see for you still, there is that foolproof way. If the electron geometry and the molecular geometry match, and all of the outer atoms have the same electronegativity, then it's nonpolar. Alright, if that's not the case, then it's polar. So this is tetrahedral electron geometry, tetrahedral molecular geometry, and I know I'm doing that fast. It's going to take you time before you can see that for yourself quickly. So the electron geometry and the molecular geometry match, but the outer atoms are not the same electronegativity. They're different. If I swap those hydrogens for fluorines all the way around, there we go. For fluorines, it's tetrahedral, tetrahedral, but all of the atoms are the same. So this is nonpolar. There is no molecular dipole. I'm showing that bond dipoles, they're pretty large arrows, but there's no yellow arrow there. It's a nonpolar molecule. And this applies to, lots of things. So BF3 versus NH3, right? NH3 is polar because it's this trigonal pyramid shape. It's tetrahedral electron geometry, trigonal pyramidal molecular geometry, so they don't match. It's automatically polar because of that. But you can kind of see the NH bonds kind of all point upwards, right? I mean, they're kind of pointing in all different directions, but overall upwards, and that's where that yellow arrow comes from. But BF3 or BH3, BF3, let's try that one. This one is trigonal planar. It's flat, right? It doesn't have the lone pair on the boron like the nitrogen does. And so because it's flat, these arrows just all cancel each other out. It's nonpolar. Using my other method, the shape, the electron geometry is trigonal planar, the molecular geometry is trigonal planar, same, and the outer atoms are the same electronegativity, so it's nonpolar. Okay. Done that to death, hopefully. All right. Honestly, understanding the polarity of these shapes of molecules is kind of like the very beginning of organic chemistry. So if you ever are going to take more chemistry, this is an important thing to remember. Okay. So we covered this. We covered water. We covered ammonia. We covered all these. So we talked about some of the weirder shapes. So BF3. Remember, boron is one of the exceptions to the octet rule. Boron and beryllium, they don't need a full octet to be stable. So the fact that there's only 6 electrons around this B is okay. So that's just one of the ones you just remember that that's okay. Here we go. These are the 2 tetrahedral shapes. One's polar, one's nonpolar. And that's just because of what's attached to the carbon. So it's not completely symmetrical. And then I think we looked at this as well. So let's go right past this. I don't know if we want to do any more of these. Let's do one more, just for fun. So ClO3 minus. This is called chlorate. You don't have to know that, but let's do the Lewis structure for this thing. And there's a lot to this one. This one can be complicated. So let's start with the electron count. 7 electrons for fluorine. 6 electrons for the oxygens. So there's 3 oxygens plus we add an electron because of the negative charge. Every negative gets an extra electron. Every positive we remove an electron. So 8 plus 18 is 26. And then we'll do our skeletal structure. Doesn't matter what direction you put them, whether it's shape or more symmetrical or what doesn't matter. That comes next. That comes after this. So 6 electrons. 2, 4, 6 have been used up. We've got 20 left. And we'll do the octet rule for the outer atoms. 6 plus 2 is 8. 6 plus 2 is 8. And then 6 more here. We've got 2 left. We'll do the octet rule for the central atom. 2, 4, 6. I need 2 more. Perfect. Done? Maybe? So this is a valid Lewis structure. This is one Lewis structure that you could write. And don't forget to put the brackets around it with the minus sign to show the charge. What we should be doing, though, is kind of recognizing that, hey, maybe there's a bunch of formal charges in here. And one of the ways I know that there are is oxygen usually has 2 bonds when it's normal, when it's got 0 formal charge. If I were to calculate the formal charge in this oxygen, it's going to be 6, which is the number of valence electrons, the original ones, right? Minus 6 lone pairs electrons, minus half the number of bonding electrons, there's 2. So there's a minus 1 formal charge on all of these oxygens. They're all basically the same. And remember that the formal charges have to add up to the overall charge. So these have to add up somehow to minus 1. That means this has got a formal charge too. And you can figure it out. But let's calculate it the regular way. So 7 valence electrons minus 2 lone pair electrons minus half the number of bonding electrons. So there's 6 there. 3 bonds, 6 electrons in those bonds. So 7 minus 2 is 5, minus 3 is 2. So this has got a plus 2 formal charge on it. So hopefully we've learned a little bit from the formal charge rules. That's not ideal. That's pretty bad. So is there a way to get rid of some of these formal charges? Well, we could try sharing electrons to see if that gets rid of some of the formal charges. We know that oxygen likes to have 2 bonds to it. So what if we did something like moved, here I'll use a different color so it stands out. Move this lone pair here, and move this lone pair here, and just 2 of them right now. So if I did that, what would happen is I'd still have that lone pair in the chlorine. I'd still have this is untouched, but I'd have a double bond now here, and I'd have a double bond here. And you might immediately look at that and say, wait, that's breaking the octet rule. 2, 4, 6, 8, 10, 12 electrons are on the chlorine. And it is, but chlorine is a period 3 element. Anything in row 3 has electrons, the valence electrons are in shell 3. And shell 3, n is equal to 3, that's when the d orbitals start. Alright, when n is 3, L can be 2. So those d orbitals are there, they're empty, but they're there. And so that's where you can put the extra electrons. Alright, there's more than 8, well the extras go in the d orbitals. If I recalculate all the formal charges, I'm going to spoil it. I don't want to say here calculating. That's 0, that's 0. The chlorine, let's do that one. It's a little odd. 7 minus 2 lone pairs minus half the number of bonding. 2, 4, 6, 8, 10. So 7 minus 2 minus 5 is 0. So everything is 0 except for this oxygen. It's still a minus 1, which is fine, because remember that the overall charge still has to be a minus 1. So this is actually a better Lewis structure than that, because of the formal charge rule. We're going to come back to why we know that that's the correct structure, besides just knowing these rules. You know, it's kind of an arbitrary thing. But that's the better structure. Now, whether you got this structure or this structure, it's not going to affect the shape that we figured out, because the shape, well, it's not going to affect the shape. So, to find the shape, we look at groupings of electrons around that central atom. So there's 1, 2, 3, 4 groups of electrons around the chlorine, electron domains if you prefer that name. 4 groups. So the electron geometry, when you have 4 groups, that means tetrahedral. electron geometry. So the electrons are going to force this thing into that overall tetrahedral shape. But not every electron group is a bonding group. That's not one. So the molecular geometry is tetrahedral with one part cut off, which is what we call trigonal pyramid, pyramidal. So really what this looks like is you've got a chlorine with a lone pair, and then you've got, and this is going to be hard to draw with the wedge bond notation, but you've got this like this, and then you've got that. And these two are double bonds. I can't really show them because you can't really show a double bond with this, but that's the shape it's going to take. So is it polar? I mean, it's already an ion, but the ion itself is polar too. So, or is it? Yeah, it is. The oxygen's 3.5, the chlorine is 3.0, and so this thing is going to go in this direction. The dipole moment is going to go in this direction. Okay. So this is one of the more complicated ones. So yeah, with the formal charges, that is the correct Lewis structure. But either one of these will give you the correct shape. So as long as you get the connections right, you get the numbers of electrons correct, make sure you draw all of them. All 26 need to be present, so they're present, both of them. Just one is a little bit better than the other. Okay. I think I asked you guys this question before, right? Well, let me ask again. Is this polar or nonpolar? So, most people say it's polar, and I think I did ask this question, but if you've forgotten, it's okay. I've forgotten. It's polar. And this is like a trick question, or not really a trick question, but this is a question that makes you need to think a little bit about it, because just drawing the dipole moments on this picture is not going to give you the correct answer. It looks like the fluorines are on opposite sides of the molecule. The dipole moments cancel each other out. But that's not the shape of the molecule. The shape of the molecule is that tetrahedral shape. That's just the Lewis structure, and it's not even a good one because it's missing lone pairs in the fluorine. So it's not showing the shape, and with the shape, you can tell that you should hopefully be able to tell that it is a polar molecule. It would look like this. So the dipole moment definitely points in that direction, kind of towards that side of the molecule. So this is the partial negative side, that is the partial positive side. Okay. Are we good with polarity? I think everybody's like, all right, enough. Okay. So let's come back to these resonance structures that we've been drawing. We started, we have this concept of how to figure out if a certain resonance structure is better than another. We use Lewis structures, and then we draw the resonance structures, and then we use formal charges to figure out the best structure. Okay? But there's going to be, and I think I spoiled this a little bit, but there's going to be cases where you'll have resonance structures that look like equivalent, meaning there's no way to decide one is better than the other. They have the same formal charges. One doesn't look like it has an advantage over the other. And that's the case for benzene. So this is the molecule benzene. So it's a subtle distinction, but the double bonds have just swapped the carbons that they're They're in between. So we're not turning the molecule in this case. That carbon is still that carbon. We're just moving the second pair of electrons, the double bond part, to a different set of carbons. So which one's better? Well, it turns out they're the same. And if I were to ask you on a test, well, what is the bond order between a carbon-carbon and the carbon-carbon bond in this molecule? You wouldn't say bond order 1, and you wouldn't say bond order 2. You would actually say something that is between bond order 1 and 2. So something like 1.5. So how do we figure that out? Well, first of all, this comes back to another way that we show this benzene. So let me come back to this. The true picture of what benzene looks like is not like this, nor is it like this. Both of these are actually incorrect. The true picture is something in between those two. So instead of saying it's, I wish that I knew what the next picture was, I forgot. Instead, it should be drawn something like this, where there is a 1 and a little bit bond, 1 and a partial bond between all of the carbons. That's what we really should be drawing. But again, this is a Lewis structure. Lewis structures are supposed to show the location of every electron. They're supposed to show the correct numbers of electrons. This is not a good Lewis structure. So we don't draw it like this. What we have to do is stick with these resonance structures. We have to draw this and draw that and say, well, you should know what the true picture is like, but we can only draw it like this. So this is actually a failing of Lewis structures. We're limited by what we're doing. So a lot of people actually draw benzene like this. And again, this is not a valid Lewis structure, but this is a very common practice in chemistry. So instead of showing double bonds, so this pair of electrons, that pair of electrons, and that pair of electrons, we show basically the electrons all over this carbon ring. And we call that the resonant hybrid, or resonance hybrid. It's the picture of all of the resonance structures that are valid, mixed together into one. And again, it's a better picture of what the molecule really looks like at the molecular level, or how it acts at the molecular level, but it's just not a good Lewis structure, so you can't really formally draw that when you're drawing Lewis structures. But this is very well accepted, so you'll see this a lot. So how do we calculate the bond order? Well, the bond order is just an average of the structures. So for benzene, it's 1.5, and it's the average of 3 double bonds and 3 single bonds. So, basic idea is, and I don't really like how they set it up on the screen here, but I've got, let's look at one of these. Let's look at one of these resonance structures. So here's one of the resonance structures, and when you compare the resonance structure, actually I'm going to draw both of them. Let's try both of them. So this is the single, that's the double. So when you calculate what an average bond order is between the bonds between the carbons that are doing resonance, first of all, you got to look at which bonds are doing the resonance. Well, it's not the carbon-hydrogen bonds. We can ignore those. It's these carbon-carbon bonds. Okay, those are the ones that are changing. And then to do the average, you basically look at every single bond. Well, in one structure only. So just pick one and look at that. Well, there's a double bond there. There's a single bond there. There's a double bond there. There's a single bond there. A double bond there. And a single bond there. That's all the bonds. How many bonds are there? There's 6 bonds. That's the calculation. That's the basic average. So if you do this, you get 1.5. So that's why they did it like this. 3 bonds are double, 3 bonds are single, divided by 6. So the true picture is not there's a double, single bond. The true picture is that resonance hybrid. Every carbon-carbon bond is actually a 1.5 bond. Each bond is actually bond order 1.5. So remember that resonance is only moving the electrons around. You're not moving any of the atoms around. You're not creating a new connection. So you don't move the nuclei, the atom parts, okay, or the proton parts. So we say that, well, as far as the electrons that we can move around, these electrons are delocalized, meaning that we can't tie them down to a specific bond. They're moving around the molecule itself. So the single bond part, right, like this bond here, that's local. And in this double bond, the single bond, the part that connects the carbon to the carbon, that's localized. But the double bond part, this second pair of electrons, these are the ones that are moving around this carbon ring. They're delocalized. They're not local to a specific bond. So this word delocalized, you're going to use that a lot in chemistry to describe electrons, yeah. And that should be not a new idea. Quantum mechanics states that we really don't know the absolute positions of electrons. So this concept of, hey, we found the electrons between these two bonds, that's I wouldn't say it's a rare thing, but that's an unusual thing, right? So this concept of the electrons being found anywhere in the atom, that's a more quantum mechanics picture. All right, we can't really exactly know where the electrons are going to be. Okay, but this is kind of what we're looking at here, this is kind of a happy middle ground between not knowing anything and knowing too much, okay? So again, whenever you find these resonance structures, and I know we did this and this was resonance, but we're talking about resonance structures where the different resonance structures are approximately the same kind of priority. They have the same formal charges. There's no way to distinguish one's better than the other. In those cases, you're going to have delocalized electrons, and the true picture of your molecule is going to be some combination of the resonance structures. That's called the resonant hybrid. So, let's try this. Let's do nitrate ion. And if you've forgotten what nitrate ion is, it is NO3 minus 1. What is the bond order between the nitrogen and oxygen in nitrate? There's a lot to do. If you don't remember what the Lewis structure is, draw the Lewis structure, figure out what the resonance structures are, if there's any, and then see if you can figure out that average bond order. Give you a second. Or a minute, I should say. These are decent test questions. At least this one is. getting wetter right now. Okay. So, hopefully you've gotten this far, somewhere close to this, drawing the nitrate Lewis structure. You should run out of electrons before you complete the octet for the middle. So that means you're going to have to share from the oxygen. So instead of putting lone pairs on the oxygen, we'll move one back to the middle. Now, here's the clue that there's resonance structures. Why would I pick this oxygen over this one or this one? Well, that's it. I shouldn't. All three are likely. So I could share from this oxygen, or I could share from this, or I could share from this, which means that there's three different resonance structures. There's one where I share from the bottom left, and I might as well. I'll do lone pairs for this one. I'm not going to do it for the rest because it's annoying. I could share from the top, or I could share from the bottom right. All right, so double bond O gets two lone pairs. Single bond O gets 3 lone pairs. So these are the 3 Lewis structures, and these are what are called resonance structures. You'll often see these double-headed arrows pointing between the different resonance structures. That's a very common thing to do in chemistry as well. So that's kind of what the Lewis structure looks like. I'm ignoring the bracket charge thing, but we don't need to put that here. So if we calculate a bond order, we just need to look at one of these Lewis structures. So let's look at this one. And the bonds where the electrons are moving around are just these 3. So we're looking at these 3 bonds. One of them is a double bond. The other is a single. And the third one is a single bond. And that's out of 3 bonds. So 4 out of 3 is 1 1/3, 1.33. So that's the bond order. So it's not, here we go, yeah. It is not just a single bond and a double bond, but the bond order of all of the nitrogen-oxygen bonds are technically 1 1/3 bond. So really, if you had to draw it, it would be something like where, how do you draw a third of a bond versus a half of a bond? There's no distinction, right? It's 1 and a little bit, 1 and a little bit. That's what the bond order is, each of these bonds is. So how do we verify that? Like, how do we know that these resonance structures are true? Well, we know what an average nitrogen-oxygen single bond looks like. Its bond length, its bond strength. We know what an average nitrogen-oxygen double bond looks like. It's shorter, it's stronger. Well, when we measure the bond length and bond strength in nitrate ion, it's somewhere in between those two, which kind of proves that it's this partial 1 1/3 bond instead of a solid 1 or a solid double bond. So resonance does a few things. For one thing, it's a band-aid. It fixes our Lewis structure, right? Because if I drew one of these Lewis structures and I said, hey, this is what it looks like, it's not really what it looks like. I don't have a double bond here and a single bond here. Single bonds are weaker than double bonds. It's not as weak as a single bond. These bonds are actually 1 1/3 bonds. So that's what resonance does. It complicates things, but you have to understand this concept to understand in your head, oh, this Lewis structure is not the whole picture. We have to kind of understand a little bit beyond what we're drawing. We need to understand, hey, there's resonance structures here. These resonance structures combine and make these resonance hybrids, and they have unusual bond orders. Okay. There it is right there. Okay. So what is the average formal charge for each? And what is the formal charge on the hybrid structure? So, if you're used to doing formal charges, you could do them on this one, and then you can kind of extrapolate what the rest of them are. So that's the regular oxygen. This one has a formal charge of 0. These oxygens, we did those over there. These oxygens are -1 formal charges. And the nitrogen has a plus formal charge. So Okay, 4 bonds to nitrogen, it's got a +1 formal charge. So over here, these have the minus, this has the minus, that has the minus. Okay? That's what the formal charge on all of these oxygens are. So what's the formal charge on the hybrid structure? Well, the nitrogen's easy. It's always +1. On average, it's +1. But what about this oxygen? Well, out of 3 of the structures, 2 of them are -1, and 1 of them is a 0. So we've got a -1, a -1, and a 0 out of the 3 different structures. The average is -2/3. So the formal charge on each oxygen is -2/3. Not -1, -2/3. So go back to the rules on formal charge. The rule for formal charge is kind of we want the smallest formal charge. That'll help create the more stable structure. And a -2/3 charge is a little bit better than a -1 charge. So that's another benefit of these resonant hybrids, of having resonance, is you can distribute the formal charge a little bit more and make them smaller. Okay. There you go. All right. So how do we explain resonance with atomic orbital theory? And it's a little hard to do that. We'll try. So we're going to get into now something called valence bond theory, and this is basically a model or a theory that describes how these covalent bonds are formed using the orbitals that we've learned already. Also, how we get these weird shapes. So how do we get this trigonal pyramidal shape, where these bond angles are 1 or 9.5, or not even 1 or 9.5, they're distorted. They're like less than 1 or 9.5 sometimes. They're not standard angles. How do we get all these distorted shapes using these very standard orbitals we learned about? So let's start from the beginning. We'll start with the simplest model, and that's just 2 hydrogens. So a hydrogen has a 1s orbital. That's all it's got in its valence shell. So when 2 hydrogen atoms come into contact, the way they share electrons is for their 1s orbitals, which each have an electron in them, right? That's where their electron is sitting in the 1s orbital. To share their electrons, their orbitals have to overlap. And that's how a covalent bond forms between 2 hydrogen atoms. This is the basis of, this is the simplest kind of bond in valence bond theory. You can do the same kind of overlap with a p orbital too. So if you have, for instance, hydrogen and fluorine, we know that HF is a molecule that exists. We can draw the Lewis structure. Just looks like pretty simple. There's HF. So this bond, well, how is it formed? Well, the p orbital on fluorine is the orbital that is missing an electron, right? When you do the orbital diagram for fluorine, the s orbital is filled, but the p orbital, the p subshell, has 1 electron opening. It's 1 electron missing, so it needs a shared electron from the hydrogen. Well, the hydrogen's 1s with its 1 electron, and it comes in, it overlaps with the p orbital. And remember this, there's a p orbital, it's got this dumbbell shape with a 0 electron density in the middle. So one of those p orbitals is going to be pointing right at the hydrogen, and it'll overlap with the s orbital, and there you go. There's a region of overlap. You can share electrons in that overlap area. And that is how the covalent bond between hydrogen and fluorine is formed. Pretty simple so far. You can do the same with 2 fluorine atoms. So the fluorine, let me remind you about this unpaired electron, right? Make sure we're on the same page. When I draw fluorine's molecular orbital diagram, You've got the inner electrons, the 1s, which we don't really touch. And then you've got the valence electrons, the 2s and the 2p, so this is full. And then this has 7 electrons. 1, 2, 3, 4, 5, 6, 7. So that empty p orbital, that's the one that's doing the bonding. It needs another electron in there. It needs to complete its octet. So that p orbital is going to overlap the p orbital from another fluorine. And they will overlap. And just like that, make a covalent bond between 2 fluorines. So that's simple. When you make just a simple binary covalent compound, 2 atoms. But how do you make these more complicated shapes? How do you go from an orbitals that are spherical, these s orbitals, and these p orbitals that are 90-degree angles, right? There's 3 p orbitals on each atom. There's one that goes this way, one goes this way, and one goes this way. How do you go from those rigid angles to these weird shapes, tetrahedral, 1 and 9.5? This is where it gets a little bit tricky. So, remember what an orbital really is. How do we know these orbitals? Well, they're basically equations, right? They're solutions to the Schrodinger wave equation. They are wave functions. That's what we call these equations. These wave functions represent, or we can derive the orbitals from these wave functions. So it's just math equations. And, okay, so, well, what can we do with those? All right. We can mix the atomic orbitals that we are comfortable with, that we know, the s, the p orbitals. We can mix them together and create new equations. So I don't know if you've done any kind of algebra where you combine 2 equations and you get new equations out of it. Well, that's essentially what we're doing. There's a math called linear algebra, which is more specifically what this is. And if you mix 2 equations together, you'll get 2 new equations. So that's what we're going to do. And I don't have a movie queued up, because I know that it's missing. Yeah, it was missing. So here's what's going to happen. I'm going to show you how this works. Ignore this for a second. Let's start with our basic tetrahedral structure. So, methane. We'll keep it simple, we'll use hydrogen. Kind of looks like that. The angle's a little bit tweaked here. This is tetrahedral. All of the angles here are 1 and 9.5 degrees. And there's no way the regular s and p orbitals will bend. Like, you can't get a p orbital, like all the p orbitals to bend downwards to connect to these hydrogens. So instead what they're going to do is they're going to mix together to create new orbitals. And when you have this tetrahedral shape, what the orbitals do is they hybridize. That's the term we use, which basically means mix together to create new orbitals. And these new orbitals, they're called hybrid orbitals. And the label we give them, so we have the s orbital on the carbon, and we have the p orbitals on the carbon, right? This is the 2s, these are the 2p orbitals. What these 4 orbitals together will do is mix together and create these, what are called sp3 hybrid orbitals. They're called sp3 because literally it's the s and 3 of the p orbitals mixing together. And if I mix 4 of these orbitals together, I will get 4 new orbitals. So the number of orbitals you mix together, it corresponds to the number of new hybrid orbitals you get. And coincidentally, not coincidentally, but through math, when you mix these 4 shapes together, you'll get new orbitals that point in exactly the tetrahedral directions you were looking for. So this s and these p's all mix together to make these new shapes. So notice that these orbitals kind of look like p orbitals. They have two lobes to them, but in reality, one lobe is really big, one lobe is really small. And the lobe that is the big one, that points towards the atoms that it's going to overlap with. So notice that they're pointing in the tetrahedral directions. You've got the three base parts, and then you've got the one on top. And they are perfectly angled to create these tetrahedral shapes. So in essence, anytime you have tetrahedral electron geometry, you have sp3 hybridization. So sp3 hybrid orbitals are required to make this tetrahedral shape. And again, it's probably not satisfying, the explanation I gave you, but it's really just math. These equations that we use to represent these orbitals are just being mixed together, and they generate new equations. And these new equations give you these shapes. Okay? So this is really the bonding picture, the valence bond theory picture for methane. So carbon has these sp3 hybrid orbitals that point towards the 1s orbitals on hydrogen, and they overlap. Let me show you one more thing. This is what happens to the energy. I shouldn't have erased it when I had before. So here's carbon. Originally, carbon had, and I'm just going to draw the valence orbitals. Originally, carbon had the 2s and the 2p orbitals. And in terms of electrons, there were 1, 2, 3, 4 electrons. 4 valence electrons for carbon. Now, this is atomic carbon when it's not doing anything. When it makes this bond with, when it makes this molecule, CH4, what these things do are hybridize, right? These will hybridize together. These will mix together to create these new hybrid orbitals. Do you see any difference between these 4 hybrid orbitals? They're all practically identical. They're just pointing in different directions. These new orbitals actually have the same energy. So we don't call them s orbitals or p orbitals anymore. We call them sp3 hybrid orbitals. And since they all have the same energy, what do you do with electrons in degenerate orbitals? You put 1 in each first. So these 4 electrons now go 1, 2, 3, 4. And this is exactly how you make a bond between 4 different atoms. You've got 4 unpaired electrons, 1 for each hydrogen. And they're all the same energy, so there's like no distinction between them. So again, this is one theory on how we can describe bonding, how we can describe what's happening in covalent bonding. This is called valence bond theory. And this part of valence bond theory, we have this idea called hybridization of orbitals. And it works pretty well. It's actually, organic chemistry is all over this stuff. All right, so it doesn't matter whether it's got 4 bonds or 3 bonds or 2 bonds. As long as it's tetrahedral, electron geometry, you're going to get these sp3 hybrids. So the same happens for ammonia, the same happens for water. So notice that in ammonia, that's nitrogen. The original nitrogen's orbital energy diagram is this. It's got 5 valence electrons, right? S, the 2s and 2p. Those orbitals hybridize. They mix together and make sp3 hybrids. All of them do. All of them mix together, make these sp3 hybrid orbitals. And now here's your 5 valence orbitals from nitrogen. Notice that one of them is already paired up. That's where the lone pair is. That's why there's only 3 bonds to nitrogen, because nitrogen only has 3 unpaired electrons left for bonding. So this is kind of the why this happens now, we can see. All right, we're not just giving you these arbitrary rules and these weird ways to set up Lewis structures. We're giving you the why now as to why it only makes 3 bonds. All right, and you can say why using this valence bond theory model. Okay. Here's water. Water has the same an oxygen at the middle, and the oxygen has two s and two p orbitals, just like nitrogen does. But it's got 6 valence electrons. So 1, 2, 3, 4, 5, 6. And when you hybridize, so first of all, we know from the Lewis structure water makes this tetrahedral electron geometry. Why does it do that? Well, if it does that, you get sp3 hybrids. They're all the same energy. There go your 1, 2, 3, 4, 5, 6 electrons, and there's only 2 unpaired electrons for bonding. That's why it only makes 2 bonds. 1 to each hydrogen, it's H2O, and that's it. It's not H3O. It's just H2O. So, this is kind of the why. Why the Lewis structure works the way it does. Why you make these bonds. This is just one way to describe why, though. We're going to look at another way, maybe at the end of class, maybe on Wednesday. So, sp3 hybridization, is that the only hybridization that exists? No. There's other ways to hybridize orbitals, and it depends on the geometry. So this is, again, we need to understand the shape of the molecule very, very well. So, BF3 and formaldehyde, CH2O. Let me show you what they look like. So formaldehyde looks like this. Pay attention to the carbon in the middle. The shape around that carbon is trigonal planar. Same thing with BF3, it's trigonal planar. It's 3 groups of electrons. It's not like tetrahedral, which is 4 groups of electrons. It's 3. So when you get trigonal planar electron geometry, you have a different kind of hybridization. It's now sp2 hybridization. Hopefully you can guess by the name that the s and only 2 of the p orbitals mix together. So one of the p orbitals is left alone. We'll come back to that. So the s and just 2 of the p orbitals mix together. And when you do that, you get, again, 1, 2, 3 orbitals mixed together to make 3 hybrid orbitals. These hybrid orbitals are pointing in the right direction for trigonal planar, these 120 degree bond angles. So again, they're called sp2 hybrid orbitals because only one of the s and 2 of the p orbitals mix together. All right, we know it's sp2 when it's trigonal planar. Trigonal planar triggers sp2 hybridization. We can keep going down the line. There's sp hybridization too. You might think it's not as necessary, but it is. With sp hybridization, this is what you get when you have a linear shape. Linear meaning something in the middle and one thing on either side. All right, not just a single 2-atom bond, but like a 3-atom bond. So sp, it's just the s and just one of the p orbitals mixed together. And I think this is a lot easier to see, but you get one lobe pointing this way, one lobe pointing that way, and that's it. 2 hybrid orbitals. So linear shapes trigger the sp hybridization. So CO2 does this. It's linear, and then there's beryllium chloride does that too. That's a weird one, but it does that. So, bottom line, sp3 hybridization, it's an s and 3 p's mixed together. That's 4 orbitals. So you get 4 sp3 hybrids. With sp2 hybridization, you get 3. With sp hybridization, you only get 2 of them. All right, and they correspond to the shapes, the electron geometry of the molecule. There you go. So linear, trigonal planar, tetrahedral. Now, let's focus on the p orbitals that were not involved in hybridization, right? So in the tetrahedral shape, all the p orbitals got used up. They all got hybridized. There's nothing left. But for trigonal planar, we left one of those p orbitals alone. And for linear, there were 2 p orbitals that were left alone. So what happens to those? So let's look at C2H4. And I'm going to draw this on the board. So with C2H4, I'm going to just draw the Lewis structure really quickly. looks like this. It's a carbon with a double bond in it. And if you look at one of the carbons, there's 1, 2, 3 groups around that carbon. That's trigonal planar. Same thing with this carbon, trigonal planar. So trigonal planar creates sp2 hybrid orbitals. So in order to create this 120 degree angle bonds, you need to have sp3 hybridization. So on this carbon, you've got a hybrid orbital pointing in that direction. You've got a hybrid orbital pointing in that direction. And you've got a hybrid orbital pointing to the left. Those are the 3 sp2 hybrid orbitals. There's 1, 2, 3. All right, I'm going to put a little C in the middle just to remind you that that's one of the carbons. And how do they? What bonds do they make? Well, this carbon is exactly the same. This is trigonal planar electron geometry. So that carbon does sp2 hybridization as well. So one orbital is pointing that way, one pointing that way, and the other one's pointing that way. And there's a carbon right in the middle there too. So you can see that there's one overlap. That's one bond with the carbon. What's going on over here? Well, I'm going to draw them in black. There's the hydrogens with their s orbitals. I'll put a label there. There's the 1s from hydrogen. There's another hydrogen here. There's another hydrogen here. Another hydrogen here. So all of those hydrogens have 1s orbitals. They're overlapping with the sp2 hybrid orbitals on each carbon. And those are creating the first bond. So the first bond in every single bond here. So notice that there's 2 bonds between carbons. So where does the second bond come from? The first bond comes from this overlap. Well, the second bond comes from the unused p orbitals. So there is on each carbon one unused p orbital on each carbon. And they are actually pointing in and out of the board right now. So we're looking at this thing flat, head on, like this. The p orbitals are actually, the unused p orbitals are kind of going in and out of the board. So one lobe is sticking out of the board, the other lobe is sticking right into the board. So if I turn this thing sideways, all right, I'm going to try to do as best perspective as I can. If I turn this thing sideways, I'm going to use my little perspective notation here. So I've got, and then there's a bond here, but I'm going to ignore that for a second. There is, let me put this a little closer. Hold on. A little closer, sorry. There we go. So there is an orbital, a p orbital, that is kind of sticking up like this on each carbon. So these are the unused p orbitals. They're not hybridized. One comes from one carbon, the other comes from the other carbon. Notice that they are oriented to overlap, and I'm going to exaggerate it a little bit now. They're going to overlap side to side now. And they overlap in 2 spots, up at the top and up at the bottom. This is where the second bond comes from. This double bond means there's 2 bonds. The first bond comes from the overlap of the sp2 hybrid orbitals on each carbon. The second bond comes from the overlap of the p orbitals. So let's talk about these overlaps here. When you do this head-on overlap, and that's the one we've been kind of looking at mostly, this head-on overlap like this is a kind of a bond we call a sigma bond. Now, it's not a single bond, it's a different word. Sigma is the Greek letter. And it just describes the type of orbital overlap that occurs to create that bond. So any kind of overlap where there's only overlap in one position, one place. I guess the best way to describe it is a head-on overlap. That's a sigma bond. Whenever there's a side-to-side overlap like this, and there's overlap in 2 locations on the same 2 orbitals, That's called a pi bond. So basically, if I describe the bonding, there's a bunch of sigma bonds. That's a sigma bond, that's sigma, that's sigma, that's sigma, that's sigma. Anytime there's an overlap between two orbitals, and it only overlaps in one position. And then this overlap here is the pi bond. So again, I'm turning this molecule sideways like that and looking at it sideways, and out sideways, and I can see the p orbitals that are sticking in and out, up and down. And they overlap in two spots, and that's a pi bond. So, pi bond. And we can generalize this. It turns out that every single bond that you draw on a Lewis structure, all single bonds, are sigma bonds. I should write that, sigma. There we go. Let me write that out too, sigma. You know what that means. So, all single bonds are sigma bonds. So whenever you draw a Lewis structure, you can point out, hey, that's a sigma bond, that's sigma. One of those bonds is a sigma bond, that's sigma, that's sigma. Double bonds and triple bonds are where you start getting pi bonds. So whenever I see a double bond, I know one of the bonds is sigma. The second bond that makes the double part is a pi bond. Okay? And that's kind of where this comes from. It comes from the leftover p orbitals that are not hybridized. All right. Okay. So, let's see. Yeah. So let's kind of go through, take a break, at least from me talking. Let's go to page 262 in your workbook. Actually, it's on 263, and let's do questions 1 through 5, just to kind of take a break, read a little bit if you need to, if you don't understand what I said, and just kind of look at these shapes of orbitals yourself, make sure it makes sense. You can describe the kind of bonding you see. Let me see the timing here. All right. Okay. We should talk just really briefly about these. Hopefully they make kind of sense. With hydrogen, the only overlap you get is the s orbitals, because that's all there are. In hydrogen fluoride, if you do the electron configuration, the orbital diagram configuration, the hydrogen has an unpaired electron in the s orbital, the fluorine has an unpaired electron in the p orbital. So that's it. It's an s and a p. With carbon monoxide, well, originally, we're not going to get into the hybrid orbitals here, but in terms of what orbitals are involved, it's the s and the p's only. That's it, because there's no d orbitals that exist. And with fluorine, it's going to be mostly the p orbitals. Although you could argue the s and the p orbitals too. But that's it. I mean, we're not talking about anything fancy, no d orbitals. Most of the orbitals we're going to work with are just s and p. We're not going to do anything more complicated. There's a whole class called inorganic chemistry. You take it as a senior year as a chemistry major, and that's when you start going hardcore into d orbitals, and sometimes f orbitals, but usually d orbitals. They get complicated. The transition metals make everything a lot harder. So we're going to stick to simple s and p. Sigma bonds are head-to-head. Pi bonds are side-to-side. What is the characteristic shape? So if you think about the bond of a sigma bond, the bond lies along the bonding axis. If I draw a line between these two carbons, that overlap occurs right on that line. It's on the internuclear axis, basically. Whereas the bond in pi bonds, here's the bond, or here's the carbon-carbon line. That's the axis between the two nuclei. The bonds occur off the nuclear axis. So the overlap is up above and below it. So it's a little different. And then, so where is the electron density? So the electron density is on the axis in sigma bonds, and it's off the axis, above and below the bonds in pi bonds. And then, if the bond is a single bond is, what type of bond is it? Well, it's pretty much only going to be a sigma bond if it's a single bond. Yes?
I had a question about, it was number 3. I understand, where it is, but how should we answer that? Like, it says, what is the characteristic shape? So how would we word that?
So, I guess what you want to do is you want to look back at these pictures here, and whatever the shape, however you can describe this, I mean, you can say that there is I guess the bond the bond shape is just a single overlap, whereas the shape of the bond here is two overlapping areas that are separated by a region with no overlap. I mean, it's whatever makes sense in your head. That's it.
There's not names for it. It's not.
No, there's no meaning. It's just to keep it straight in your head. That's it. It's just a tool to help you remember it. That's it.
It's okay.
If you can describe it, it sets it in your mind better. That's kind of the idea.
Okay.
So again, question 5. I say it quickly sometimes. So single bonds are normally sigma bonds. Okay, so it's kind of hard to hear the distinction, but so single describes the fact that it's a single pair of electrons. Sigma describes the kind of overlap that's that is done between orbitals to create that bond. Okay, and it's pretty simple. Single bonds are generally sigma bonds. So sigma, 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 all of them are sigma bonds, and all of them actually happen to be single bonds. The double bond in the middle, half of it is a sigma bond, half of it is pi bond. All right. Okay. So while we're mostly going to see pi bonds with p orbitals. You can do them with d orbitals too. If you remember some of the shapes of the d orbitals, they had d orbitals that kind of looked like this. Sorry, that's really bad looking. But you can do these two area overlaps with d orbitals very easily. So pi bonds exist with d orbitals too. Again, we're not going to worry about it. I'm just pointing out that there's a rich kind of bonding that you're going to see eventually. And there's more bonds than this. There's not just sigma and pi, but we're not going to get into the others. There's a delta bond, there's weird stuff. Okay. So there you go, sigma bonds, head-to-head overlap. That's a sigma bond, that's a sigma bond. That hydrogen is a sigma bond. And it doesn't have to be between like regular atomic orbitals, it can be between hybrid orbitals too. Hybrid and atomic, and then hybrid and hybrid. As long as it overlaps in one spot. So if you didn't like my drawing, here's a slightly better drawing of ethylene. So first we're showing all of the orbitals. So we have the sp2 on this carbon, there's 3 of them. And then the unused p orbital. And here are the sp2s on this carbon and the unused p orbital, and then the s orbitals on the hydrogen. And so you're seeing all of these sigma bonds there. And then after you remove the sigma bonds, so here's the sigma bonds, let's take those orbitals away. What's left are the p orbitals, and those p orbitals, and this is distorted, they're showing that they are able to overlap side to side like this. And that is the second bond in that double bond. Yeah, this is just another view of it. So, yeah, so if you look at it on top, there is the sp2 hybrid orbitals. There's 3 of them. There's 3 of them here. And they're doing their sigma bonds with each other and with the hydrogens. And then if you turn it sideways, there's the p orbitals. So there's different ways to kind of visualize those p orbitals overlapping, but that's kind of what you get. Okay. And again, this is just yet another view of it. That's kind of more like what I did. But yeah, same view. So sigma bonding, and then the pi bonding, and then this is all of it together. So you can see that the pi bonding puts electron density kind of out of the plane of the molecule. It's kind of like not where the bonds are. It's kind of above and below, which actually helps us understand reactivity of this thing. Ethylene is a precursor to lots of things. It's used to help make fruit ripen. It's used to make plastics. It's very, very important molecule in chemistry. In industry, I should say. All right. So again, same thing. Sigma bonds, and then the pi bonds. Okay. So let's look at ethyne, better known as acetylene. Ethyne is C2H2. And I'm going to remind you, because it's not a, it is, right here, there it is, the Lewis structure of this thing. It's got a triple bond between the 2 carbons, and hydrogens on the other side. If you describe the shape around this carbon, one group of electrons on this side, one group of electrons on this side, that's 2. That's the linear shape around that carbon. And linear around this carbon as well. So linear. The hybridization you get from linear electron geometries is sp hybridization. So 1s and, well, there's only 1s. The s and one of the p orbitals mixed together, and that's it. Meaning that 2 of the p orbitals are left alone on each carbon. So what you get here is like this. This is after hybridization. You get an sp hybrid pointing that way. You get an sp hybrid pointing that way. So this one bonds with the hydrogen. This one bonds with the other sp on the carbon, on the opposite carbon. So this makes your sigma bond. That makes a sigma bond with the hydrogen's s orbital. There it is. Sigma, sigma, sigma. Now the leftover p orbitals, there's one that's pointing up and down, and there's one that's pointing in and out. That one, that's kind of perspective drawn there. And those, there's 2 sets on each. They make 2 pi bonds. So one that overlaps, this way and this way. So top and bottom, right here. And then the other 2 go in and out, and overlap side to side as well, and make this bulb in front, and then there's a bulb in back that you can't see. But there's 2 sets of pi bonds there. And that's where the triple bond comes from. The triple bond is a sigma bond between these two hybrid orbitals plus 2 pi bonds. Triple bond, 3 bonds. So whenever you see a triple bond, automatically in your head, you don't have to think of this, but you should remember a triple bond is a sigma bond and 2 pi bonds mixed together. How do you get this triple bond? Well, you have to have this sp hybridization in order to get that. You need to have these 2 p orbitals that you can do pi bonding with. So only one of the p orbitals mixes together with the s orbital. Makes the sp hybrid orbitals, 2 of them, and that's it. Down here, this is just complicated kind of description of what 2 orbitals make a certain bond. So the sigma bond between a carbon sp and another carbon sp hybrid. The pi bond is made with a carbon p orbital, the 2p, and a carbon 2p. There's a second pi bond made with a carbon 2p and a carbon 2p. And then there's sigma bonds made with the carbon sp hybrid and the hydrogen 1s orbital. And then on the other side, there's the same thing. Starting to get a little convoluted, a little bit. But I think this is as far as we're going to go when it comes to like complicated bonding models. But let's come back to benzene. Since with Lewis structures, we understood that benzene, even though we draw a Lewis structure for it, it's not correct. That's not correct. That's not correct. It's the combination of these two that is really the true picture. So what does the bonding look like for it to really look like that? So forget about everything except for this top part here, okay? So if you go back to what benzene's Lewis structure is, real quick. Around any one carbon, what's the shape? There's 1, 2, 3 groups of electrons around that carbon. Every other carbon is the same. 3 groups of electrons. 3 groups of electrons is trigonal planar. So every carbon in that molecule is trigonal planar. Trigonal planar means that the hybridization is automatically going to be sp2. And don't forget, you write this down. It's kind of a cheat sheet in your head. Tetrahedral is sp3. Trigonal planar is sp2, and linear makes sp hybrid orbitals. Okay? So sp2 for all those carbons. So look at the top left here. What you're seeing is every carbon has 3 sp2 hybrids. All right? You mix an s and 2 p's, you'll get 3 new hybrid orbitals. They're called sp2 hybrid orbitals, and there's 3 of them. So 1, 2, 3. And one points to the hydrogen, the other 2 point to the other carbons in the ring. Every carbon does that. So that's where the basic framework for this ring comes from. Right? Those are all sigma bonds. And they make the first bond in that molecule. Now, when you have sp2 hybrid orbitals, the fact that there's only sp2 means one of the p orbitals is not used up. It's left alone. Every one of these carbons has a p orbital that is sticking in and out of the board, going this way, in and out. So if we kind of rotate this a little bit and look at it in perspective, that's what they look like. They're kind of in and out of this hexagon. Now notice that they're all set up to kind of be side to side. And that's what they're all doing. They're all doing side-to-side overlap. Now, is it fair to say that they're only going to do side-to-side with the one neighboring carbon and they're going to ignore the other neighbor? Well, that's what the Lewis structure shows, right? We put a double bond between carbon, put a double bond between these. We alternate. But in reality, it doesn't make sense to look at it that way, because all of these p orbitals, they're all able to overlap with each other. And really, this is the true picture of what you're looking at. All of these p orbitals are all interacting with each other. And that's why the double bonds, the electrons that make the second bond in all of these double bonds. So there's 6 electrons, right? 3 double bonds, 6 electrons. there's 6 electrons that are able to just move around this ring in this giant overlap of bonds here, of orbitals. So that's why these electrons are considered to be delocalized. They're not stuck between these 2 carbons and these 2 carbons and these 2 carbons like that. That's not what they look like. They're kind of allowed to go wherever they want. And we can see that now with this bonding picture. So this is kind of like the explanation for why we have these resonant hybrids. Is because of the way the orbitals overlap with each other. The electrons are allowed to kind of freely move around. And it's because of the nature of the pi bond. Alright, so that's benzene. Here's another picture of it. So the p orbitals just make this gigantic overlap of orbitals like this. And so those electrons can go where they want. Now the electrons in the sigma bonds are stuck. Those electrons in the sigma bonds are stuck where they are. They have to be between those 2 atoms because there's nowhere else for them to go. But in the pi bonds, they can kind of move around. And if you do any kind of calculations on where the electron density is, that's what the computer models suggest too. So you can see that this red spot, you can't see it on the bottom, but it is there too. It's just kind of, there's no like red spots on between 2 carbons and that's it. It's kind of all the way around the ring. So there it is. That's the true picture of benzene. That's why we put the little circle. When we draw benzene, we draw it like this a lot, instead of with the double bond, double bond, double bond. Because the electrons that make those double bonds are delocalized. They move around the ring. That's what the circle represents. Turns out nitrate does the same thing. So we did this Lewis structure. We did show there was a resonance structure between. There's 3 different resonance structures. And we determined through, formal charges and through bond averages that the average bond is 1 1/3. That's what the resonant hybrids show. So how does that work? Why does it work like that? Well, again, this nitrogen is an sp2 hybridized, has sp2 hybridized orbitals. There's a trigonal planar shape around this nitrogen. 3 groups of electrons, trigonal planar, sp2. So there's one unused p orbital, and that p orbital on the nitrogen that's sticking kind of this way, and so if you rotate it sideways, kind of sticking that way, can interact with the p orbitals and all the oxygens bound to it. And it does this thing where the electrons can kind of go wherever they want, and that's why you don't have 1 double bond and 2 single bonds. It's just a mix of 1 1/3. Okay, so we didn't talk about d orbitals, but because we're not really going to cover these shapes in the final. But if you're curious, octahedral and trigonal bipyramidal, those more those shapes that you need for when you expand the octet. In order to get those shapes, you need to include d orbitals in your hybridizations. So it's not just an s and 3p that mix together. You add a d orbital. And then to make octahedral, you add 2 d orbitals in addition to your p orbitals and your s orbitals. Don't worry about it. I'm not going to quiz you on that, but that's how you make those shapes. So again, focus on these. Tetrahedral automatically makes sp3 hybridized orbitals on your central atom. Trigonal planar, sp2, linear, sp. You don't have to talk about hybridization on the external atoms. You can, but it's not necessary. You only have to worry about this hybridization idea on that central atom, okay? So, let's come back and talk about something like, let's do one of these, I guess. So, N2O. Pretty sure I did this one as a Lewis structure. So N2O, let me not use red as it shows well. N2O is nitrous oxide, laughing gas, I'm just going to draw the resonance structure, or the Lewis structure. Hold on. I'm not going to go through the whole setup. The proper Lewis structure is this. So that's what the Lewis structure is. If you do it correctly, you do the correct formal charges. There are other Lewis structures, but this is the correct one, because this is the one where the formal charges make sense. So if we talk about hybridization, so what is the hybridization on this central atom? Well, first let's talk about the electron geometry. So the electron geometry is linear. Why? Because there's two groups of electrons on either side. One on one side, one on the other. If it's linear, then it automatically is sp hybridization. And I just erased my cheat sheet. Oh well. Sp hybridization on that central atom. OF2. We can do that one from scratch. So 6 electrons, 7 electrons, and there's 2 of them. And it's neutral, so that's it. 14 plus 6 is 20. O in the middle, fluorines on either side for now. That's 4 electrons used up. Got 16 left. Octet rule of the outer atoms first. 1, 2, 3, 4, 5, 6, plus the 2 here makes 8. 1, 2, 3, 4, 5, 6, plus the 2 here makes 8. And I've got to do the octet rule for the central atom. I have some left. Perfect. 2, 4. I need 4 more. 1, 2, 3, 4. That's it. Easy. So the shape of this thing, I've got 1, 2, 3, 4 groups of electrons around that central atom. So the electron geometry is tetrahedral. That's it. You have to memorize these things. Tetrahedral. If you want to do the molecular geometry, we can, but we don't need that for this. But molecular geometry is bent, or V-shaped if you prefer it, but bent works too. Because there is 2 bonding groups on those 4 electron groups. But we only need to look at the tetrahedral part to know that the hybridization on this oxygen is sp3 hybridization. Okay. So over here, we can just quickly look. This N, what's the hybridization? It's sp3 because there's 1, 2, 3, 4 groups, tetrahedral. So it's got to be sp3. The carbon, sp3. The oxygen, sp3. 1, 2, 3, 4. What about the carbon here? Yeah, sp2. So there's 1, 2, 3 groups around the carbon, so it's sp2. So I mean, everything that led up to it seems complicated, I think, for some people, but the end result, understanding the hybridization, what is the hybridization? I think that's easy to do once you know the shape. You can figure out the shape, you can figure out the hybridization very easily. So, I can let you guys answer this one on the clicker. How many sigma bonds and how many pi bonds are there total in this molecule? This is a good test question too. One today. the votes are mostly B, some D. So honestly, the best way to do it is count the total bonds. So 1, 2, 3, 4, 5, 6, 7. 7 sigma bonds. Because every single one of those bonds has one sigma bond in it. And then how many double bonds? Well, there's 1, so that's the second part of that bond is a pi bond. So there's 7 sigma bonds and 1 pi bond. So again, it was, yeah, the person who did D was correct. So that double bond is both a sigma and a pi together. Okay? So there's 2 bonds in there, so there has to be 2 sets of overlaps. Yeah?
There are only 6 single bonds?
Did I count? 1, 2, 3, 4, 5, 6. Yeah, 6 single bonds.
Yeah.
And 1 double bond, but a double bond contains a sigma
and
bond
okay,
and a
right.
pi bond. Yeah. So every bond is at least a sigma bond.
Yeah.
Okay. So, tricky part. Okay, I'm glad everybody tried this one and understood their mistake now. So there's all the plain sigma bonds, but there is an extra one that is in the pi bond, and then that pi, well, in that double bond, and the double bond has a pi bond in it too. Okay. So what 2 orbitals are overlapping to make the bond shown by that arrow? So what 2 orbitals are overlapping in that double bond there? That make a sigma bond. So in that double bond, we're making a sigma bond. What 2 orbitals are overlapping to make a sigma bond? Stop it there. Sorry if I cut anybody off. Oh, it's a little bit all over the place. A, B, and E. So the answer is E. So again, pi bonds are going to be just the p orbitals. Okay, so that's a quick shortcut. Pi bonds are going to be p orbitals and only, and that's it. So the sigma bond is the more complicated one. So we need to look at what orbitals are in each of these carbons, and that comes from the shape. So the shape on this carbon, a pair of electrons, or a group of electrons here, a group of electrons here, that's it, 2 groups. Means linear. So this carbon has sp hybrids. This carbon though, 1, 2, 3 groups. Trigonal planar. Trigonal planar is sp2. So this thing has sp hybrids, this thing has sp2 hybrids. And those are the 2 orbitals overlapping to make that sigma bond. There's an sp from this carbon pointing that way, and an sp2 from this carbon pointing that way. Of course, there's another sp2 here, and another sp2 pointing that way, and on this carbon, the other sp is pointing that way. But that's what's overlapping in that particular sigma bond. How many of each bond total are there in that structure? How many sigma, how many pi? All right, more confident this time, I think. Yes, so definitely B. All right, good. Relearn their lesson. So we're done for today. You understood those points. You're in good shape. We'll do our final review on Wednesday. We'll do a quiz at the beginning that is just Lewis structures and shapes. We'll skip the dipole moment stuff for now. Well, until the final. And we'll try to maybe introduce medical orbital theory and then do some review. Okay? FYI, The Batman and IMAX. Oh my god, that's a good movie. Go see it if you have a chance. It's 3 hours long though, so don't get a drink.
It was too long.
It's pretty long.
I'm not super committed to the whole Batman thing, so a lot of my friends who really liked Batman before liked it, but I haven't seen most of the other ones. So like, it was a good movie. It wasn't like.
They're all different. The DCEU movies are cornball cheese, but you know, if you're a fan, it's fine. The Nolan movies are great. This one was just as good, but in a different way.
Yeah.
It's I like it.
It's better than Uncharted.
Yeah, video game movies.
Sweet.
It's,
Except for Jumanji. Jumanji.
Oh, I love Jumanji. I love Jumanji. It's stupid, but I liked it.
But it gets away with it because it's stupid.
Even the remakes are pretty good. So.
Thank you.
Yeah, take it easy.
I may have done this wrong, but so is this not linear because it has that third group? So it's trigonal?
Trigonal planar.
I
Yep.
know. And then
So the shape, the molecular shape is going to be, so, you know, you start with trigonal planar, but then one of those positions is just a lone pair. So with your left is bent. Yeah.
I think I wrote that right. I drew it wrong,
Yeah.
though.
Okay.
But it's, so then it's so the actual thing would be that like.
Just
this-
showing, yeah, it's bent a little bit. There's like a approximately 120-degree angle between them.
And do you, label the charges on the drawings or just the Lewis
No, just the
structure?
Lewis structure is fine. The drawings are just, I mean, so these have to be a certain way. These are very stylistic, you know, as long as you show the proper shape is fine.
Okay. And this one, number 10, I accidentally did twice because I read this wrong. I did it like as C-I.
Oh, yeah,
I didn't
yeah,
realize
okay,
what it
that's
was.
fine.
So I've done it probably wrong there and then I did it again.
Oh yeah,
over
that's
here.
actually fair. The font's pretty close to. Yeah.
So I don't know
we need to use a sans serif font, which is like without the little things on it.
I guess I didn't draw this though, and this is, you had this.
I had it earlier.
here,
It's
but it's the
it looks like that.
C. Oh wow, okay, so it's just, oh, the top is
So
unpaired.
because of there's a lone pair, it's tetrahedral electron geometry, and then when you take off, you know, if there's this would be tetrahedral if there's something else here, but now there's nothing, just a lone pair, so it's trigonal pyramidal.
Okay.
Or trigonal pyramid, whatever you'd like to say.
This part I'm understanding a lot more than the, I'm still having problems drawing the, like the orbitals, filling the S and P.
Oh, the orbital diagrams?
Yeah, I'm still having a little trouble, but I went back into the homework and I think on the online homework.
Okay.
I can, it actually helps me once I sit and put the time.
Okay. Well, you know, if we can get done with the lab, save some questions for lab if you want, or if you can make it on a Thursday morning, that too. But yeah, get your questions out before
Yeah.
the end of the week. You know.
Yeah, what else was I gonna ask? Oh, I sent an email, but it was too late, I think. It was like 11:30, 11 or something today, about asking, maybe if I could look at the key again, the pink
Oh,
key.
yeah, you did. Great. Yeah, let me go grab it. Right back. And then be right back.
Thank you. Oh, wait, it's not, there's 6.
No, sorry, the lab manager put the stuff away.
Oh, okay.
And I don't know where he keeps the keys, so.
Oh, thanks.
If there's a specific one I can help you with, I can help you with a couple if you need it.
Thanks. I think it's okay. I'll just I'm just gonna. I think I figured some things out after class actually.
Okay.
So, thank you. I wasn't sure about counting the extra unpaired electrons in the first